All right, so we're talking about ATP production. More specifically, we're talking about anaerobic ATP production. We've already talked about the ATP PCR system, which we call the immediate energy system, because when we run out of ATP, the first system that kicks in immediately to replace that ATP is the ATP PCR system. So it's the first system to kick in. It's very quick, it's very simple. It produces a lot of ATP in a short period of time, but it only lasts for 10 to 15 seconds. So as the ATP PCR system is less able to replace ATP, we need to get ATP from another system. And so the next system that kicks in as the primary system is called glycolysis, which is another one of the anaerobic systems. All right, so glycolysis is often called the short-term energy system because it is not fatigue resistant. Okay, and what that means is that it cannot produce ATP for long periods of time. It's a short-term system, so its function is to produce ATP for short periods of time, and we'll talk more about that. It is an anaerobic system, so it occurs in the cytoplasm. Okay, anaerobic systems occur in the cytoplasm. Okay, the function of glycolysis is to make ATP using glucose. Okay, and all glucose originates from your food. Okay, you eat carbohydrate and you turn that carbohydrate into glucose. Okay, some of that glucose is going to be stored in the liver. Some of that glucose is going to be stored in the muscle, and some of that glucose is going to remain in your bloodstream. Okay, that's called your glucose pool. Okay, so right now you have muscle glycogen, which is glucose stored in the muscle. You have liver glycogen, which is glucose stored in the liver, and you have some glucose in your blood. Okay, we call that your glucose pool. As your muscle uses glucose, okay, glucose from the glucose pool is going to go into your muscle cells. And as glucose leaves the bloodstream, we need to replace that glucose in order to keep your blood glucose levels steady. So what happens is the liver glycogen will break down into glucose, and that glucose will enter the glucose pool. It'll enter your bloodstream and maintain your glucose pool at a steady level. And we'll talk more about glucose levels and the maintenance of glucose levels in Chapter 4. Okay, we also have already within the muscle cell, we have some muscle glycogen, which can break down right there within the muscle cell and provide glucose for glycolysis. Okay, so there's where the glucose can come from. And the reality is that at any given time, the glucose that's going through glycolysis originated from all three of these locations. So glycolysis is a process of chemical reactions, and each chemical reaction includes the use of an enzyme. One of the enzymes is called PFK. That's the only enzyme I'm going to require you to know. This is called the rate-limiting enzyme. Okay, because based on the activity of this enzyme, the rate that glycolysis occurs is determined. Okay, so in other words, the rate of glycolysis is heavily reliant upon the activity of PFK. Okay, so it helps determine the rate. So let's see what it looks like. So this is figure 2.7 from your book. And as you can see here, there are lots of chemical reactions. Okay? Remember that a chemical reaction involves a substrate going through a chemical process and becoming a different substrate. So here we have lots and lots of substrates. Okay? So for the purposes of this class, I don't want you to focus on all of the detail of glycolysis. I want to point you in the direction of what I think is the essential information to understand and to grasp first. And those of you who go on to take further exercise physiology courses, you will learn a new layer or an additional layer of information. But for now, we're going to back off some of this information and focus on what I think is essential at this point. So what I'm going to do is I'm going to cross out some of these substrates, because at this point I don't think it's important to know the names of these substrates. Okay? I still want you to understand that there are multiple substrates involved, but it's not important to know what their names are. Okay? So there are some substrates left here that I do want you to know. Okay, so here we have glucose. More specifically, we have blood glucose. Okay, so this is coming in from a capillary. You have glucose in your capillary blood, which leaves. Okay, and so here we have a muscle cell. And remember, this is happening in the cytoplasm. Okay, so when glucose leaves your capillary, it enters cells, okay, for our purposes, muscle cells. And so you do have blood glucose coming into the muscle cell, coming into glycolysis. Okay. Another substrate I want you to know is glycogen. And again, because we're in a muscle cell, this is muscle glycogen. Okay. We also have something called glucose 6 phosphate, glucose 1 phosphate, 3-phosphoglyceraldehyde, and there's 2 of them, pyruvate, and there's 2 of those, and lactic acid, and there's 2 of those. Okay, so we'll get to those in a minute. But your first assignment is going to be to draw glycolysis, and I want to make sure that you don't include unnecessary details, because it's going to keep your attention away from the details that I really think you need to know right now. Okay. So glycolysis starts with glucose 6 phosphate. Okay, this is the start of glycolysis. So let's go backwards and let's see, how do we get to glucose 6 phosphate? And the process is different depending on whether we start with blood glucose or muscle glycogen. Okay, so first let's talk about, what do we do with blood glucose? How does blood glucose become glucose 6 phosphate? Okay, because once we've got glucose 6 phosphate, we can begin the process of glycolysis. So how do we get to that point? All right, so we have blood glucose. Okay. Here we have the muscle cell. Here we have the capillary. Okay. The glucose from the blood enters the muscle cell. Okay. And before it can go to glycolysis, it needs to become glucose 6 phosphate. So what happens is, if you look carefully at the drawing, it shows that an ATP gets broken down to an ADP. Okay? So in the process of converting glucose into glucose 6, we've used an ATP. Okay? Remember that the purpose of this process is to make ATP. But in the early stages of glycolysis, we need to invest some ATP before we make it. Okay, so let me show you a little more about what's going on here. So remember that when ATP breaks down to ADP, it releases a free phosphate and it releases some energy. What's happening there is that the phosphate that originated on the ATP is being phosphorylated and added to the glucose. So basically you're binding this phosphate to this glucose. Okay? And we end up with something called glucose 6-phosphate. The energy is being used to create that bond. Okay? Because if we take glucose and we add a phosphate and we make glucose 6-phosphate, we had to create a bond. And in order to create a bond, we need energy. Okay? We need energy for anabolic reactions. So the energy from ATP was used to bind that phosphate onto the glucose. Now where does the 6 come in? 6 does not mean that there are 6 phosphates. 6 just means that the phosphate, it's just telling you where the phosphate was attached to the glucose. So the phosphate was attached to glucose in the number 6 position, and therefore we call it glucose 6-phosphate. Okay? So we've started here with the blood glucose. We used an ATP. We took the phosphate from that ATP, we phosphorylated it, put it onto the glucose, and we used the energy released from that ATP to do that. Okay, so right now we are -1 ATP. So we're trying to make ATP, but we've invested 1. We're -1. Now we have glucose 6-phosphate. Now the process of glycolysis can occur. Okay? And remember, we're not going to worry about these. Okay? Let's talk about the other side of this, which is, what if we start with muscle glycogen? Okay? So you're breaking down glycogen within the muscle. When you break it down, you release it in a form that's not pure glucose. You release it in something called glucose 1-phosphate. Okay? And if you remember what I told you, the 1 doesn't mean that there's 1 phosphate, it means it's in the number 1 position. Okay? So basically what happens here is you take muscle glycogen, you've got those pearls, right? You've got all your glucose molecules strung along. You're going to release 1, but it's going to be phosphorylated. Okay? So we have a glucose 1-phosphate. We have a glucose with a phosphate connected in the number 1 position. We cannot begin glycolysis yet because glycolysis requires that phosphate to be in the number 6 position. So basically what happens from this step to this step is that we just move the phosphate. Okay, we move it from the 1 position to the 6 position, and we end up with glucose 6-phosphate. Notice that we didn't use any energy here. Okay? So at this point, we have not used any ATP. So here, on this, if we started with blood glucose, at this point we're at -1. If we start with muscle glycogen, we haven't used any. Okay? So we're at 0. We haven't made ATP, we haven't produced ATP. So either way, we have glucose 6-phosphate. That's our next step. So let's talk about what happens once we get glucose 6-phosphate. Glycolysis begins. It's going to go through a series of chemical reactions. Okay, so glucose 6 is going to become another substrate. Again, doesn't matter what that substrate's called. Then that substrate is going to become another substrate. Okay? And this is where PFK comes in. PFK is the enzyme that catalyzes this third reaction. Notice what's happening in this third reaction. We are using another ATP. Okay, so again, we're taking an ATP, we're breaking it down, we're releasing a phosphate, we are using some energy, and so now we've used another ATP. Okay, so now at this point in time, we're minus 2 ATPs, and we're at the end of step 3. Okay, so if you started from muscle glycogen, we're at minus 1. Okay. Okay. All right, so now we are at step 4. At this point, this one substrate splits into 2 substrates. Okay, so at this point, we have 2 substrates. That's what the 2 means. And the substrate is called phosphoglyceraldehyde. So we have 2 of them. That's our split. Okay, so we have 2 phosphoglyceraldehydes. We go to another step, and we've got these NADs that come in, which we'll talk about later. Then we go through step 7, and look what happens in step 7. We've created an ATP. Finally, we've created an ATP. Okay. And remember that you've got 2 of these substrates. So everything that happens from here down happens twice because you have 2 substrates. Okay, so we get 1, 2 ATP. Okay, we get 2 whether you start with blood or whether you start with muscle glycogen. At this point, we have plus 2. Okay. Then we have another reaction. Notice that in reaction 9, we produce some water. We don't need to worry about that. Okay, produce some water. And then in the 10th reaction, the final reaction of glycolysis, our final substrate is pyruvate, and we have 2 of them. Okay, remember, because everything is happening twice. We have 2 pyruvates at the end of glycolysis. Also, if you look carefully at that final step, we produced 2 ATPs. Okay, 1 ATP from this substrate and 1 from this substrate, right? Because there's 2 of them. So now what we have is 2 more ATP if you started with blood, 2 more if you started with muscle glycogen. Okay. So let's see here. So if we look at the net gain at the bottom here, you can see that if we start with blood glucose, we're minus 2, plus 2, plus 2. Okay? So our total net gain is 2. So we went through all of these processes and we ended up with 2 ATPs. Okay? We made 4, but we used 2. So we had to subtract those 2 and we end up with 2. If we come from muscle glycogen, it's just slightly different. We invest 1, we make 4, and so our final gain here is going to be 3. Okay? So we made 4, we invested 1, 4 minus 1 is 3. So we have 3 ATP. Okay? So once we go through this process, if the glucose 6 originated from muscle glycogen, at the end we have a net gain of 3 ATPs. Okay? So when you look at this assignment, basically I've asked you to draw this process without all the circles and lines all over the place. You're going to draw the substrates, only the substrates that I indicated, and you're going to draw in what's happening during these reactions. Okay? So you're going to show that we use ATP, we make it here, we make it here, and in the very end of glycolysis we end up with a substrate called pyruvate, and we have two of those. Okay? So we start with one glucose molecule, we end up with two pyruvate molecules, okay, because of this split here. Okay, so all along you have one substrate until you get here, and that one substrate splits into two identical substrates. So everything from here down happens twice because there's two substrates. So we end up with pyruvate. Okay. At the end of, once we get pyruvate, now the body can do two things with the pyruvate. Okay. This pyruvate can enter the mitochondria and go on to aerobic energy production, or it can be converted to lactic acid. Okay. So lactic acid is not actually part of glycolysis. It's one of the next steps that can occur with pyruvate. All right, so we're at the end of glycolysis. We end up with two pyruvates. Okay, that pyruvate can do one of two things. It can leave the cytoplasm, enter the mitochondria, and then go on and give us more ATP aerobically, or it can be converted to lactic acid. Okay, so one of two ways. The way that you need to think of this is that glycolysis produces pyruvate, and the mitochondria clears it. Okay, so what determines whether glycolysis becomes lactate or it goes into the mitochondria? Well, basically it has to do with how much the mitochondria can take up. Okay, so glycolysis is producing it, mitochondria is clearing it. If glycolysis produces it faster than we can clear it, right? If production is greater than clearance, we're going to end up with some excess pyruvate. And anything excess gets converted to lactic acid. Okay? So when the mitochondria cannot take up pyruvate at the rate that it's being produced, okay, so it's being produced very quickly from glycolysis, and if the mitochondria can't take it up fast enough, anything excess is going to get converted into lactate. Now, when we are doing very low intensity activity, so if we're at rest or we're doing low intensity movement, most of the pyruvate gets taken up by the mitochondria. We don't produce a whole lot of lactic acid at rest, okay, because the pyruvate's being produced at a relatively slow rate because you're not doing a lot of work. And so therefore the mitochondria can match clearance with production, and we can take up most of it, therefore we don't end up with a lot of lactic acid. However, if you start doing activity of a greater intensity, okay, you're going to need ATP at a faster rate. So glycolysis is going to happen faster, which means that pyruvate is going to be produced faster, and eventually the mitochondria is not going to be able to take it up at the rate that it's being produced. Okay? So production is going to become greater than clearance, and when that occurs, we end up with some excess pyruvate, and that has no choice but to be converted into lactic acid. Okay? So the higher the intensity, the more glycolysis produces ATP, and the more pyruvate is produced in the process. And glycolysis happens at a much faster rate than the aerobic processes in the mitochondria, so you end up with your excess pyruvate being converted into lactic acid. And this is on a continuum, so the higher the intensity, the faster and the more pyruvate is produced. The production is going to be even greater than clearance. You're going to end up with more excess pyruvate. You're going to end up with more lactic acid. Okay, so that's why when you're doing higher intensity exercise, you produce more lactic acid. Okay, because the higher the intensity, the harder it is for the mitochondria to take up the pyruvate at the rate it's being produced, and therefore more and more is going to have to be converted to lactic acid. But the body's first choice is to clear it through the mitochondria. Okay, that's number one. Okay, but anything that the mitochondria can't clear is converted to lactate.